complete row is 0, we have to go with the previous row to 0 row. We have to differentiate and get the coefficient, replace in the 0 row, proceed and complete the RH table. Okay, whenever in the RH table, this is second special case in RH table. Whenever we are doing RH table, complete row is 0 means we have to go to the previous row of 0 row, that is called auxiliary equation. The previous row to 0 row is called auxiliary equation. We have to differentiate that auxiliary equation, get the coefficient, put it in the row of zeros. Okay, replace, put it in the row of zeros, complete the RH table. Okay, complete the RH table. Definitely this case system will not be fully stable. It may be marginally stable or unstable. Whenever complete row 0 comes, okay, complete row it is 0, then it cannot be a stable system. Roots will be on imaginary axis or on the RHS also. So it can be marginally stable means roots are on the imaginary axis. Marginally stable means roots are present on y axis, j omega axis. In that case, sometimes root may come on RHS also. If at all RHS come, we will decide it is unstable. If there are only LHS and on the imaginary axis, we will say system is marginally stable. Okay, whenever row of 0 comes, there is more possibility for marginally stable on the imaginary axis roots will come. Okay, so here a characteristic equation is given. We will try to find the stability of the system. First step, we have to prepare RH table. Step 1, we have to prepare RH table. So it is s power 4, s power 3, s power 2, s power 1, s power 0. And here the first element, first term, third term, fifth term. Okay, it is 1, 3, and 2. Next, we are going with the alternate terms. Second term, fourth term, the coefficients are 1 and 2. Next, we have to calculate first 2 rows. Automatically, it will be taken from the given characteristic equation. Here, further, we have to do our calculations. 1 into 3 minus 1 into 2 divided by 1. It is 3 minus 2 by 1. It is 1 by 1. The value is 1. Okay. Next element, how to calculate? I have to calculate here. One element is present, other element is not there. We have to take it 0. Okay. Now do the calculation. 1 into 2 minus 1 into 0 divided by 1. It is 2 minus 0 by 1. The value is 2. Okay. So now you can see s power 3 row, s power 2 row, they are exactly same. S power 3 row coefficients, s power 2 row coefficients, they are exactly same. Okay. So in this case, if you go with further calculation, it will come 0. Let us see. So we have to calculate here. And now 1 into 2 minus 1 into 2 divided by 1. It is 0, 0. Okay. 2 minus 2, which is 0, divided by 1. Okay. 0 minus 1, it is 0. I am getting 0 here. No further calculation possible because elements are not there. No further calculation possible. Elements are not there. Here, in the previous case, if you see, there are further elements. In this particular case, we got an understanding that only first element is 0. Okay, there will be further elements, only first element will be 0. That is a different case. Here, only one element is there in the row, no further elements possible. So in this case, it is called as row of zeros. Okay, row of zeros. If the given characteristic equation is very big, s power 7, s power 6, s power 5, okay, s power 7, s power 6, s power 5, something is there. Lot of coefficients will come. In that case, you can find more zeros. Not only 1 0, but you can find more zeros. Okay. But in our given question, only 1 0 came, and in the row itself, only one element is there. So we cannot say it is a first element 0 in the row. It is a row of zeros. It is a row of zeros. In that particular case, just the previous row, it is called auxiliary equation. Just the previous row, it is called auxiliary equation. In short, we will take it AE. Characteristic equation means CE. Okay, characteristic equation means CE. And auxiliary equation means AE. Now, what about the auxiliary equation? What about the auxiliary equation? Just 1 minute. So the equation, we have to write it. 1 is the coefficient, then 2 is the coefficient present. You can see this is s power 2 row. Okay, this one coefficient is s power 2 row. So 1 into s square plus Alternate terms only we have to use. Okay, so s power 0, s power 1 will not come. S power 0 equal to 0. Form the auxiliary equation using the coefficients. Form the auxiliary equation using the coefficients. Coefficients are 1 and 2. Okay, so the first element will have s power 2. Okay, next element will have s power 0. Alternate powers only will come. You can see the first two rows, it is alternate powers only from the given equation we are writing. So any row, it is alternate powers only, it will come. So now this is s square plus 2 equal to 0. This is our auxiliary equation. This is our auxiliary equation. Now s square value equal to minus 2, s value equal to plus or minus square root of minus 2. Okay, and now square root minus 1 can be written as j. We are having root 2. That minus I have taken outside. Minus I have taken outside. This is plus or minus j root 2. Okay, so j means imaginary axis. J means imaginary axis. So in that case, the root is on imaginary axis. So system is marginally stable. Okay, if at all other roots are present on LHS. We will see whether how many roots are present on RHS, we will see. So here, these are S values. These are S values. So we are having S equal to plus J root 2 and S equal to minus J root 2. And these two roots are on imaginary axis. Okay, on imaginary axis or on J omega axis or on Y axis. In the pole zero diagram, X axis is called real axis, Y axis is called imaginary axis. When you go with the pole zero diagram, X axis is real axis and Y axis is J omega axis, and this is called S plane. S plane. Okay. So S is nothing but sigma plus J omega. It is complex. S is nothing but complex. Sigma plus J omega. S is nothing but complex. Why we call it complex? Sigma plus J omega, S value. So sigma is real part, J omega is imaginary part. This is S plane where we do the pole zero diagram, where we do the pole zero plot, where we do the pole zero plot. Now these are the poles. Okay, these are the poles or roots of the characteristic equation. Roots of the characteristic equation. Poles means it is for closed loop transfer function. Denominator of closed loop transfer function. Okay, the poles of closed loop transfer function are roots of characteristic equation. Closed loop transfer function poles are roots of the characteristic equation. They are present on imaginary axis. Okay, now we will see we have different we have what we have to do. We have calculated the pole locations, but the thing is we have to complete the RH table. That is yet pending. We have to complete the RH table. Okay, for that I will take the auxiliary equation as number 2. I will take the auxiliary equation as number 2. Okay, both are same. Here I can give this also as 2 because both are same, exactly same. Okay, so I will differentiate this auxiliary equation. I will differentiate the auxiliary equation with respect to S. D by ds, I have to differentiate. Okay, with respect to S. Now, if you differentiate, this becomes 2S, okay, plus 0 equal to 0, 2S equal to 0. Now, if you see what are the coefficients, what are the coefficients? This is S power 1 row. Okay, this is S power 1 row. This also I am having S power 1. The coefficient is 2. So I have to replace this 0 with the value 2. Okay, this 0 I have to replace with the coefficient 2. Okay, let this be 2a, and we are getting the coefficient for 0 row from equation 2a. From equation 2a. Okay, so we are taking the auxiliary equation. Auxiliary equation means just the previous equation to previous row to row of zeros. Okay, previous row to row of zeros is the definition for auxiliary equation. Auxiliary equation means whenever we come across 0 row, just the previous row is called auxiliary equation. That is the definition of auxiliary equation. We are taking it equation 2. Okay, then we are differentiating it. Once we differentiate, we are getting the coefficients from equation 2a. After differentiating, okay, after differentiating, we are getting equation 2a. Now that coefficients we are replacing in the 0 rows. That coefficient we are replacing in the 0 row. Okay. Now I will go with the further calculation. I will go with further calculation. Now S power 0 row I have to calculate. S power 0 row I have to calculate. It becomes 2 into 2 minus 1 into 0 divided by 2. Now it is 4 by 2, value is 2. 4 by 2, value is 2. By this, the RH table is completed. With this, RH table is completed. Now I can check the first column. Okay, first column in RH table. It is positive to positive, positive to positive. Again, positive to 2 means positive only. Again, 2 to 2, it is all positive. Okay, no sign changes in first column. No sign changes in first column. Okay, we have imaginary roots. We have roots on y-axis. Okay, so system is marginally stable. System is marginally stable. System marginally stable. This is our final answer. If at all sign changes come in the first column, if at all sign changes come, then definitely system is unstable. Okay, definitely system is unstable. Whenever row of 0 comes, never the system will be stable. Whenever a complete row becomes 0, we cannot decide the system is stable. Okay, it may be either marginally stable or it can be unstable. That we will know only when we know the location of all the roots. Location of all the roots. First column, we are not having any sign changes. Okay, so remaining roots are present on LHS. That is our conclusion. Remaining roots are present on LHS. Okay. In step 1, we completed RH table. In step 1, we completed RH table. Step 2, we are forming the auxiliary equation. Step 2, we are forming the auxiliary equation. Okay, this portion is rough. Step 2, we formed the auxiliary equation. Step 3, we completed the RH table. Step 3, we completed the RH table. Okay, and this is also rough calculation. Step 2, we are finding this complete is step 2. Okay, and this is our final conclusion. Step 3, based on the number of sign changes, based on the roots on imaginary axis, we are telling the system is marginally stable. System is marginally stable.